The shell punched through the armor with a sound the crew never heard. What they felt instead was heat. A white flash filled the interior of the tank, followed by a pressure wave that turned air into fire. Ammunition ignited instantly. Metal surfaces glowed. Paint burned. Fuel vapor caught. In a space barely large enough for 5 men to stand shoulder to shoulder, the temperature spiked beyond anything the human body could endure. Training said, "Escape immediately." Reality gave them seconds. Hands clawed for hatches that were suddenly too hot to touch. Boots slipped on the floor as smoke swallowed visibility. Someone was screaming, but inside the tank, sound collapsed into a roar of flame. If a hatch jammed, if one man hesitated, the interior became a furnace. Recovery crews would later find blackened steel hulls with everything inside fused into silence. Tank crews began to fear fire more than enemy guns. Penetration alone was survivable. Many tanks were knocked out without burning. But when ammunition ignited, survival became a race against physics. Veterans whispered about which hits you could walk away from and which you could not. The difference felt arbitrary. Some tanks burned instantly, others did not. Crews tried to read patterns in wreckage, searching for logic in chaos. Rumors spread faster than reports. Nicknames appeared, dark humor masking real dread. Tankers spoke quietly about vehicles that lit up when struck. The Sherman was winning battles. It was reliable, fast to repair, and everywhere on the battlefield. Yet inside armored units, a different reputation circulated. A fear not of defeat, but of fire. And buried in engineering reports, long before most crews understood the pattern, there was already a warning. Something inside the tank was turning penetrations into explosions. The Sherman was built to fight a modern war at industrial scale. It could cross continents, survive mud and dust, and keep moving when other machines failed. But when hit in the wrong place, the same efficiency that made it effective could trap its crew inside a burning shell. The question wasn't whether the tank worked. It did. The question was why survival depended on luck, and how long a modern army could accept that trade. The Sherman was not designed carelessly. It was designed under pressure. When the United States entered the war, the priority was not building the perfect tank. It was building enough tanks to fight a global conflict that would be decided by logistics as much as firepower. American planners believed victory would depend on mobility, reliability, and the ability to replace losses faster than the enemy. A tank sitting broken in a depot was useless. A tank that kept moving mattered more than one that looked impressive on paper. The Sherman reflected that philosophy. It was engineered for mass production. Components were standardized so factories across the country could assemble it quickly. The drivetrain emphasized mechanical simplicity. Crews could repair it in the field with tools already available. It was light enough to transport across oceans and sturdy enough to survive long marches without constant breakdowns. In a war measured by distance and supply, those traits were strategic advantages. Inside the turret and hull, every inch of space served a purpose. Ammunition had to be accessible. A tank crew firing under pressure could not waste seconds digging for shells. Designers placed rounds in side compartments, sponsons along the hull, where loaders could reach them quickly. The arrangement was efficient, compact, and easy to manufacture. On paper, it solved the problem of storing large quantities of ammunition inside a small armored vehicle. But armor is geometry as much as thickness. Enemy shells do not strike randomly. They follow predictable paths. Penetrations entering the side of the tank passed directly through the compartments where ammunition was stored. When armor failed, the projectile often reached the very material designed to explode. The result was not always immediate disaster, but when ignition occurred, it spread with brutal speed. Engineers understood the risk in abstract terms. Testing showed that internal fires were possible. Yet every design carries compromises. Moving ammunition required redesigning the hull. Redesigning the hull meant slowing production. Slowing production meant fewer tanks reaching the battlefield at the moment they were most needed. In 1942 and early 1943, the calculation favored output. The Sherman was expected to win through numbers, reliability, and tactical coordination. A tank that reached the front quickly was considered more valuable than a tank delayed by structural revision. The vulnerability was known, but it existed inside a larger equation: how to arm an expanding army fast enough to survive the opening years of a global war. That equation would soon collide with battlefield reality, because once Shermans met sustained combat, the abstract risk inside engineering reports began to appear as a pattern in burned steel. The pattern emerged slowly, then all at once. Recovery teams began noticing it first. Knocked-out Shermans did not all look the same. Some were scarred, penetrated, abandoned, but intact. Others were gutted, turrets blown open, interiors burned to bare metal. The difference was not subtle. One tank had been defeated. The other had been consumed. Field reports followed the wreckage. Crews described flashes inside the hull after penetration. Survivors spoke about heat arriving faster than thought. Medics treated burns that no amount of training could prepare a man to endure. Tank commanders started cataloging which hits produced fire and which did not. They compared angles, ranges, enemy weapons. Gradually, an uncomfortable consistency appeared. Penetrations along the sides were far more likely to ignite the tank. The fear changed behavior. Escape drills became obsession. Crews rehearsed hatch exits until muscle memory replaced panic. Some tankers rode with hatches cracked open despite the danger, choosing exposure over entrapment. Others redistributed personal gear to clear paths to escape routes. Inside armored units, survival planning took on the urgency normally reserved for combat tactics. The battlefield was teaching a lesson engineers had already suspected. Ordnance teams investigated destroyed vehicles whenever possible. They traced projectile paths through armor and into ammunition racks. Tests replicated combat conditions. Again and again, the same vulnerability appeared. Rounds stored high along the hull created a chain reaction when struck. Fire spread upward through the fighting compartment, turning the tank into a sealed furnace. The evidence was no longer theoretical. Engineers proposed a solution that required more than minor adjustment. Ammunition would be moved from the sides to the floor of the hull, below the turret basket. Instead of exposed racks, shells would be surrounded by protective compartments filled with liquid. If penetrated, the liquid would absorb heat and reduce the chance of ignition. The redesign would not make the tank invulnerable. It would give crews time. Time was everything. But implementing the change meant disrupting factories already operating at full capacity. Production lines were synchronized across multiple states. Parts suppliers fed into schedules measured in weeks. Altering the internal structure of the tank risked slowing output at a moment when every vehicle counted. Commanders faced a brutal arithmetic: protect future crews or maintain present numbers. The wreckage forced the decision. As more burned Shermans returned from the front, the cost of delay became visible in human terms. Tank units could replace machines. Replacing trained crews was harder. Experience, once lost, could not be manufactured. Veteran tankers represented months of combat knowledge that vanished in seconds when a fire reached the ammunition. Pressure shifted. Redesign moved from recommendation to priority. Factories retooled. New models incorporating the protective storage, later known as wet stowage, began reaching the battlefield in 1944. Crews greeted them with cautious skepticism. No machine promised safety, but the first reports filtered back. Penetrations that would have caused catastrophic fire now produced smoke, damage, and escape, not instant incineration. The change was measurable. Tanks were still destroyed. War did not become gentle. Yet survival rates improved sharply. Crews climbed out of knocked-out vehicles and returned to fight again. Recovery teams found damaged Shermans whose interiors remained intact. The pattern that once meant certain death began to break. The Sherman had not become invincible. It had become survivable. That distinction altered morale as much as statistics. Tankers still feared enemy guns, but the sense of inevitability surrounding fire faded. A hit was no longer a death sentence written into the machine. It was a chance, slim, imperfect, but real, to live through the impact. The battlefield had forced the tank to evolve, and the evolution proved that protection was not measured only in armor thickness, but in the seconds a crew was given to escape a burning vehicle. The redesigned Shermans did not end the danger of armored warfare. They changed its rhythm. Tanks continued to be knocked out. Armor still failed under heavy fire. Crews still faced concussion, smoke, and the violence of metal tearing open. But the sudden, all-consuming flash that had haunted early engagements became less common. Penetration no longer guaranteed immolation. Between impact and catastrophe, there was now a margin, and inside that margin lived survival. Units felt the difference almost immediately. Veteran crews began to accumulate instead of disappear. Tank formations that once cycled replacements at brutal speed stabilized as experienced soldiers returned to the line after losing vehicles. Commanders noticed that knowledge started compounding. Crews who survived hits adapted their tactics. They maneuvered differently, communicated faster, and trusted their machines enough to remain aggressive. Survivability translated directly into combat power. A tank destroyed with its crew was a total loss. A tank destroyed with survivors was a delay. The distinction reshaped how armored units absorbed damage. Maintenance teams repaired vehicles. Replacement hulls arrived. But the men who understood the battlefield stayed alive to climb into the next machine. Over time, that continuity proved as important as firepower. The Sherman's reputation evolved alongside the statistics. It was never considered perfect. Crews still criticized armor thickness, gun performance, and silhouette. Yet the fear that once defined its interior faded into a more familiar calculation. Risk balanced against reliability. Tankers trusted that if the vehicle failed, it might still release them. In combat, trust is a form of armor. The redesign also influenced doctrine. Armies began to treat crew protection as a measurable asset rather than a secondary concern. Survival was no longer framed as luck. It became an engineering objective tied directly to battlefield endurance. A tank that preserved its crew did more than save lives. It returned experience to the fight. And in a war measured by accumulation of machines, territory, and knowledge, that return mattered as much as any victory on a map. After the war, the lesson of the Sherman was not remembered as a story about a flawed tank. It was remembered as a story about adjustment under pressure. The early fires forced engineers and commanders to confront a truth that modern warfare would repeat again and again. Machines built for victory must also be built for survival. Firepower and mobility decide battles, but protection decides whether experience endures long enough to matter. A weapon that preserves its crew multiplies itself over time. A weapon that consumes them resets the learning curve with every loss. Wet stowage did more than fix a design weakness. It shifted priorities. Future armored vehicles treated ammunition storage, fire suppression, and crew escape as central features rather than secondary concerns. Survivability became measurable. Testing no longer asked only whether a tank could defeat the enemy. It asked whether the crew could live through defeat. That distinction shaped post-war doctrine across multiple armies. The Sherman's evolution showed that effectiveness is not static. It is negotiated between industry, battlefield feedback, and the willingness to change while the war is still being fought. The tank did not become legendary because it was perfect. It became significant because it learned. And that is its enduring legacy. Victory belongs not to machines that never fail, but to systems that respond before failure becomes permanent.